Okay, we have seen in the last video what is meant by EMF source, and we have mentioned that there is a real EMF source with an internal resistance and an ideal EMF source without internal resistance. Now we are going to study the current in a single loop circuit, and effectively this is not new. We have already studied this circuit before in Ohm's law. We will replace the EMF source by a simple battery B with an EMF force E, which represents the potential difference between the two terminals of the battery. And this battery is connected to a resistor R. So the electric current, according to Ohm's law, would be the potential difference E here. It was V. Okay, it is V over the resistance R. So I would be E over R. Please differentiate between E of the electromagnetic force and E of the electric field. E of the electric field is the normal E. E of the electromagnetic force is this delicate. Okay? And also, we have mentioned before that because this is a conducting wire, it is equal potential surface, so the potential at each point is the same. So effectively, the potential of this point, which is notated as positive, is higher than the potential of this point, notated by negative. So effectively, any point on this wire until we reach the resistance is higher potential, and any point in this wire is lower potential. So effectively, the higher potential on the resistor to the lower potential is going in the direction of the current. So it means that the potential is going down across the resistor, or there is something called voltage drop or potential drop from higher to lower in the same direction of the current. On the other hand, if you are talking about the battery, the potential is going from lower to higher in the same direction of the current. So this voltage increase along the battery. From the point of view of energy, we say that the dissipated power at the resistance equals I squared multiplied by R. And this power, if it is integrated with respect to time, so it will be energy or work. So the delta work in the resistance at delta t of time would be I squared R multiplied by delta t. On the other hand, the work done by the electromagnetic force is the electric potential E multiplied by the charge value delta Q. And actually, delta Q is the value of the current multiplied by delta T. Or in other words, I equal delta Q over delta T. So we can say that the work done by the battery, delta W, equal the electromagnetic force multiplied by delta Q, which can be replaced by I delta T. Now, the work done by the battery is the work dissipated in the resistance. So, the delta W, which have been calculated from the resistance, must equal the delta W, which has been calculated from the work done from the battery. So, by equating this equation with this equation, we can find out that E multiplied by R multiplied by delta T equals I squared R multiplied by delta T. If we have taken this square with this I and this delta T with this delta T, we can find out the electromagnetic force or the potential difference of the electromagnetic force equals the potential difference on the resistance I multiplied by. So, in this case, we already calculated the current in a single loop circuit by using energy method. Yes, I know actually this Ohm's law, I equal E or V over R, but this from the point of view of energy. From the point of view of potential difference, we have a rule called loop rule. This loop rule states that the algebraic sum of the changes in potential encountered in a complete traversal of any loop of a circuit must be zero. What does it mean? Simply, it means that the summation of the potential in any closed loop should equal zero. The summation of the potentials in any closed loop should equal zero. And this rule is basically known as Kirchhoff's loop or Kirchhoff's voltage law, because actually it is related to voltage or the electric potential. What does it mean? It means that we will sum the potential difference due to the electromagnetic force and the potential difference due to the current in the resistance, and this summation should equal zero. But this should take into consideration the direction of the electromagnetic force. If I'm talking about electromagnetic force and electric current, so if the electric current in the same direction of the electromagnetic force, the potential here would be positive. If I'm talking about a resistor, the potential difference at the point that where the current enters it from it is higher from the potential at the point where the current leaves it. So effectively, this positive value and this negative value, or this higher value and this lower value, so the potential difference, this minus this, is negative. So in this case, if we assume that we have point A, for example, and we said that point A has a potential VA. So V at point A plus the potential of the battery E, V at point A plus the potential of the battery E minus the voltage drop at the resistance IR would equal the potential at point A. I have started from A and returned back to A as a closed loop. So VA equals VA, we can move this with this. So actually are saying that E minus IR equals 0. Or in other words, I equal E over R. So this from the loop rule or Kirchhoff's voltage law, and this from energy method, and both of them has the same result. Maybe someone will ask, what is what? What we have new? Actually, the new here is that what will happen if I don't have a single resistor, if I have multiple resistors? What will happen if I have multiple electromagnetic force devices? So in this case, we will convert each part of the circuit as a loop, and we will try to solve each loop separately. That's not the next slide. Okay. All right. Here we are talking about a resistance rule. For a move through a resistance in the direction of the current, the change in the potential is negative I multiplied by R. So if I'm talking in a loop and the assumed current of the loop is going inside the resistance, so the potential difference from this point to this point would be negative IR. So what will happen if the current that I'll assume is in the negative direction? In this case, this point would be lower than this point. So if I'm talking about the potential difference between these 2 points, it would be positive IR for the opposite direction of the current. On the other hand, for the EMF rule, if the assumed current in the same direction of the electric potential of the EMF source, so the EMF source will be taken into consideration with positive sign. So what we are seeing, for moves through an ideal EMF device in direction of the EMF arrow, the change in the potential is positive. But for example, if I assume that the current in the opposite direction, so in this case the current enters the EMF from the positive to the negative. In this case, the value of the EMF in the loop would be negative E, not positive. Because I'm going from positive to negative, not from negative. Okay? The previous example was based on ideal EMF source. Ideal EMF source, which has an F source without internal resistance. What will be the case if I have an internal resistance? If I have an internal resistance, the EMF source would be represented as an ideal battery without any internal resistance in series with its internal resistance small r. So this is the real EMF source. Real source connected in series with a resistance small r. So if I connect this real EMF source to a resistance R, and assuming that the potential at point A is 0, V point A is 0. If we expanded this circuit, instead of closed structure or closed loop structure, to a linear structure, for example, or a linear scale. So we start with point A. At point A, the potential is 0. And going inside the EMF source, we will see there is a battery with a potential difference E. And the current here in the same direction of the EMF of this battery. So this EMF in this case would be taken into positive. So by moving from the point A to this point just after the battery, the potential difference will be changed from 0 to E. From 0 to E. This is the battery. Now the electric current is passing through the internal resistance small r. So in this case, there is a potential difference on the internal resistance equals I multiplied by small r. And this potential difference is in the opposite of the direction of the electric current. So this is higher potential and this is lower potential. So it means that I subtract from this E this IR. So along the internal resistance, I subtract the value I small r. This actually is the potential at the point B. And this B will be continuous until it reaches the resistance R. So as long as I'm along this wire, this equipotential surface, so the potential will be constant VB. Okay? Then the potential difference will be initiated on the resistance capital R equals I multiplied by capital R. And this potential difference would be going down or voltage drop. So it will go from the point VB minus I multiplied by capital R to reach the potential at point A. And actually the potential point A is 0. So this will reach this. So this graphically how the electric potential is going through the circuit. Mathematically, we can say that as a loop, the summation of the potential difference in a closed loop equals 0. This summation, when I'm talking about electric potential source in the same direction of the current, it would be positive. When I'm talking about the potential drop in resistors in the direction of current, it would be negative. So E minus I small r minus I capital R would equal 0. Potential due to electromagnetic force, potential drop due to internal resistance, potential drop due to the connected resistor. Okay, so E minus IR minus I capital R equals 0. If we have taken this minus R and this minus capital R on the other side and solved for I, we can find out I equal electromagnetic force over capital R plus small r, or the resistor plus the internal resistance of the EMF source. We shouldn't take into consideration, or we should note that if the internal resistance equals 0, we return back to the simple Ohm's law, I equal E over R, if the internal resistance equals 0. Okay? Now, what will be the case if I have different resistance connected in series? What does it mean in series? Each resistance has two terminals. Assume that this terminal 1 and this terminal 2. This terminal 1 and this terminal 2. And this terminal 1 and this terminal 2. So we can say that the resistance 1, the terminal 2 of the resistance 1 is connected to the terminal 1 of the resistance 2. And then the terminal 2 of the resistance 2 is connected to terminal 1 of the resistance 3, and so on. So in this case, we say that they are series connected. The question is, if I have a circuit composed of series resistance like this, what will be the equivalent resistance of this series combination? By meaning equivalent resistance is another resistance which can replace this combination to introduce the same current in the circuit in the presence of the same electromagnetic flux. Okay, so that's what we are seeing. Resistance in series. The resistances are connected one after another between A and B, and the potential difference is maintained across A and B by the battery. The potential differences that then exist across the resistances in this series produce identical current I in sim. Because we have these resistance are connected in series, the current flowing through resistance 1 will go from 1 to pass through resistance 2, and will go from resistance 2 to pass through resistance 3. So the current here in the series resistance is the same for all the resistors. When a potential difference V is applied across resistance connected in series, the resistance have identical current I. The sum of the potential differences across the resistance is equal to the applied potential difference V. The potential difference across the resistances, the three resistance, the total potential difference between the two terminals of the resistance equal the potential difference between the EMF source V. Resistance connected in series can be replaced with an equivalent resistance R equivalent that has the same current I and the same total potential difference V as actual resistance. The question now is, what is the equivalent resistance in this case? If we are talking about a single loop across this circuit, we say that the total potential differences along the loop would be zero, or the summation of the total potentials along this loop would be zero. The summation of the potentials across this circuit would be as follows. If I'm assuming that the current is going anti-clockwise, clockwise is going clockwise, so the electric current would be in the same direction of the electromagnetic force. So the electromagnetic force will be taken in consideration as positive. Then there is a voltage drop at resistance 1, another voltage drop at resistance 2, another voltage drop at resistance 3. Each voltage drop is I multiplied by R. So the complete potential at this loop would be E minus I1 R1 minus I R2 minus I R3, and I here is the same because the same current is flowing through the three resistance, equals 0. If we have taken these items that include I the other side and solved for I, we can say that I equal the electric potential E over R1 plus R2 plus R3. For the case of the equivalent circuit, we have the same potential, we have an equivalent resistance R equivalent, and we need to have the same current I. So for the equivalent circuit, we say that for a single loop would be E minus I R equivalent equals 0. So in this case, I equal E over R equivalent. By equating the current of the equivalent circuit to the current of the original circuit, we can say that R equivalent equals R1 plus R2 plus R3. Or in other words, if there are resistances are connected in series, the equivalent resistance would be the summation of these resistances. So R equivalent for n resistances in series is the summation of Rj, where j equals 1 to n, the number of the resistances.